And it's great to be here, great to be back in Trondheim, catch up with some old friends. I used to live in Trondheim, so it's like coming home again. I'm going to talk about a little bit of a provocative title perhaps. If 2.5 degrees is easy, why is 2 degrees so hard? And hopefully throughout the presentation I'll explain why that is the case, or why I believe that is the case. It's a session on climate risk, and the presentation is going to be a bit risky because I've not done this presentation before. It's a bit of a variation of an old presentation. Some new slides, some new material, so hopefully it works well. And you're going to be the first in the world to see something or to hear about. So this afternoon we have a commentary coming out in Nature. It's under embargo until 7 p.m. tonight. I have a copy here if you want to look. And completely coincidentally, I'm going to be talking about pretty much the same topics as in that commentary. And I'll mention that a few times as we go through. So, if 2.5 degrees is easy, why is 2 degrees so hard? I'm going to use a lot of figures. They're all going to be pretty much the same. It's going to have carbon dioxide emissions on the vertical axis. It's global emissions, hundreds of billions of tonnes, big numbers. It goes negative. This grey part down the bottom is where we'll see some negative numbers. You're taking carbon out of the air. And the horizontal axis is time running from 1900 up to 2100, so about 200 years. And I'm pretty much going to keep the same graph and put some different exciting things on it. So the first exciting thing is our current emissions, or historical emissions. And over the last 100 years or so, emissions have grown continuously. Initially, back in around 1900, most of the emissions were coming from land use change, cutting down trees to use biomass, which we used for our energy back then. And then came coal, and then oil, and now gas. We have rapid growth of solar and wind, electric vehicles being deployed, but still those are not enough to displace fossil fuels. So fossil fuels keep growing, emissions keep growing. Population is growing, economic activity is growing. That means energy use is growing, and most of the new energy supply is still supplied by fossil fuels. So emissions will keep going up. That's led to around about 1 degree of global warming. We're seeing impacts of that already. Perhaps the biggest disaster is we can't go skiing this year in Oslo. So we're worried about these impacts, and we want to do something about it, but we're not sure how much we're going to do about it. That means the future is somewhat uncertain, and we use scenarios to explore those uncertainties. So here are 150 or so different scenarios, ranging from quite low-end Paris-compliant emission scenarios, all the way up to really high-end scenarios if we do absolutely nothing about climate. So if you're a decision maker, or you're an investor, or a policy maker, what do you do with these scenarios? And I'm going to try and talk through this figure and explain a little bit. And I'll break out parts of these scenarios and explain some groups of them in a bit more detail. So first of all, there's a bunch of scenarios which are often used called no policy scenarios. They're like a baseline. So you assume that there's absolutely no climate policy. So in the world today, we do have some climate policies. Some countries have strong policies, some countries have weak policies, some countries have none. But overall, there is some climate policy effect. So these are a rather hypothetical scenario if we do nothing. So there's about 30 or so scenarios here. I won't explain so much where they come from, but different modelling groups using different socioeconomic assumptions. They span from quite a low end. If you can't see it, I just point out some baseline scenarios with no climate policy will lead to a peak and decline in emissions. So if we don't do much about climate, depending on the way socioeconomics are and the way technology goes, we may reduce emissions anyway. At the other end of the extreme, there's a high-end scenario for those of you that know the lingo, RCP 8.5. It's a particular scenario that's used quite a lot in climate modelling to look at climate impacts in the future. It's the most prevalent scenario in climate modelling. That's extremely high-end. So you assume there's no climate policy. You assume the world loves fossil fuels and wants to burn fossil fuels. It requires an acceleration of coal use, actually, even though coal use might be peaking today. So this is a very high-end scenario, quite an unlikely scenario, but it's the most prevalent scenario used in a lot of climate analysis. And this is essentially what this article is about tonight, that comes out tonight. So there's quite a range, and the bold line there is the sort of middle of the road, if you like, average baseline scenario. In reality, we do have some climate policy. These are a bunch of scenarios where we have some sort of weak climate policy. The climate policy will get stronger as you go from the high to the low. If you look at most studies that try and estimate where emissions are going, where the Paris Agreement emission pledges might take us, those studies sort of suggest something around about 3 degrees, which means you're somewhere around this brown-yellow sort of line. And actually I see Sveta here from DNVGL, they have their scenario, which falls somewhere around maybe the yellow, perhaps a bit closer to the brown line, that sort of area. So with a little bit of climate policy, this is where emissions may go. We could even get quite close to 2 degrees with just weak climate policy. To get all the way down to 0 is quite difficult, and I'll come back to that in a minute. But climate impacts at 2.5, 3 degrees are still pretty severe, so we want to go much further. And these are Paris compliance scenarios. You can't quite see the rapid scale of the changes in these scenarios here based on the format of the figure here. The purple lines are 1.5 scenarios, the blue lines 2 degree scenarios, a little bit less than 2 degrees actually. Just to give you an idea, the 1.5 degree scenarios, you have to reduce global emissions by about 50% in a decade. That's everyone, not just Norway, not just Europe. Includes the US and China, India, global emissions, 50% down in a decade. Hit zero emissions, or zero net emissions by about 2050, and then after that you're sucking carbon out of the atmosphere. These scenarios are extreme. Every country has to do everything humanly possible to try and solve the problem. Then you might get one of these 1.5 or 2 degree scenarios. So that sort of scopes out the space a little bit on what these scenarios involve, and I'll dig into a few more details in a minute. But you've got a bit of an idea. I was talking about some scenarios which are a bit more likely. Some of the extremes are sort of less likely, and I'll touch on that again. But I want to come back to a little bit of a sort of physical reasoning why some of these scenarios are a little bit harder than some of the other scenarios. And to do that, I'm going to use what's known as the carbon budget. I'm going to do it in a quite conceptual way and get a little bit more complex as we go along. So the carbon budget is a quite interesting concept for many reasons. If you go out and take measurements of the temperature and you estimate how much carbon you've put in the atmosphere, the total amount of carbon, that's the horizontal axis here, temperature on the vertical axis, and you do the same in models, you run your model forward and see where things go, and then you plot temperature against cumulative emissions, you basically get a straight line, which is pretty amazing. The climate system's got lots of non-linearities in it, but at the aggregate level, it has this quite linear behaviour. There are some uncertainties, of course. There's uncertainty in the data. Some model runs will have a slightly different slope, or there might be a little bit of curvature in that line or something like that. But the big picture is you basically have a linear relationship between temperature and total cumulative emissions. And this is where the concept of the carbon budget comes from. What this means is if you emit any more carbon, every tonne of carbon you emit, there'll be a temperature increase. And that temperature increase is permanent. This is one unusual thing about carbon dioxide as a pollutant, is it's basically permanent. It's a cumulative pollutant. So air pollution, let's say sulfur dioxide, if you stop driving your car, that pollution stops and it will get eventually washed out of the atmosphere with rain or weather or whatever. Carbon dioxide, you stop driving your car and that effect lasts forever. This is one of the reasons that climate is such a hard problem to solve. But what it means is if you want to stop the temperature rising, you have to stop emitting CO2. So you have to get zero emissions. And this is where the concept of the carbon budget comes from. Essentially, the carbon budget is how much carbon you've emitted until the point you don't emit any more carbon. So if we look at what's happened in history, this is all a little bit approximate because I've just drawn a straight line on a figure. It's not actual exact data. We're up a little bit over 1 degrees of warming already. We've emitted about 2 trillion tonnes of carbon, which is that sort of grey area there. And that's just that sort of number put there. If you want to go to 1.5 degrees, we can just emit a little bit more. So there's not that much more. We've emitted a lot of carbon already, which is the grey, a little bit more carbon, and we'll go over 1.5 degrees. You will get different estimates depending on the different ways you define things. This is 600 billion tonnes, 50% probability for those that know that sort of lingo. Some of the lower carbon budgets use a 66% probability. I won't go into the weeds there, just to mention that for those of you that know. If you want to go to 2 degrees, or if you maybe don't want to, but you end up at 2 degrees, you can emit more carbon than 1.5 degrees, obviously. But when you compare it to the 1.5 degree remaining budget, it's quite a bit larger. It's about 2.5 times larger. So even though 1.5 might be really hard, 2 degrees, you've got a lot more breathing space. 2.5 degrees, you have even more breathing space again. But if you go all the way up to, say, 4 degrees, which is, say, 3 degrees above today's temperatures, you can emit an awful lot of carbon. And this is something that we tend to forget about. So this is how much carbon we've emitted already. So, basically double that again, maybe even triple that. That's what it takes to get to 4 degrees. You have to burn a lot of carbon. So it turns out that it's actually quite hard to get to these really high temperatures, and it's quite hard to get to these low temperatures. So that was a quite complex figure. It was a risky figure. I'm not sure whether it was going to work. And so I'm going to do it in text. So 5 degrees is really hard, or 4 degrees, because we'd basically have to reverse our climate policies. We'd have to stop the cost declines in solar and wind. We'd have to stop electric vehicles. We don't like them anymore. Trump, who's trying to get rid of coal as much as he can, he's trying to bring back coal as fast as he can in the US. The harder he tries, the faster coal seems to go away. No one is crazy enough to invest in coal. You have to reverse all that to get a 4 or 5 degree world. 3 degrees, in quotes, maybe is easy. So even the weak policies that we have today, with the technology, cost declines and so on, weak policies may get us to 3 degrees already. So we should see that as good news, because we can build on that and accelerate and go faster. 2.5 degrees may not be so hard. Clean technologies are getting cheaper. Technologies might get deployed. There's some attitudes changing, social movements and so on. And so maybe 2.5 degrees is not so hard. The challenge is to get to zero emissions, to get all carbon out of the system so temperatures will stabilise. That's going to be the hardest part. And 1.5 degrees is really hard, practically impossible, because you're pretty much there. Some estimates we're at 1.2 degrees, your face is against the wall, basically, you can't go any further. So these really ambitious targets get really hard again. So, and this is almost my last slide, coming back to a sort of a risk assessment, trying to put this in a more risk framing. This is sort of just summarising essentially what I've said. This is a probability distribution. It's very stylised, just approximate. Probability over here, temperature along the bottom. So 3 degrees, as I've sort of been describing, is sort of where current policies or stated policies, emission pledges currently take us. And this is what I've called the most likely outcome. If you're interested in physical risks, so you invest in infrastructure, you're worried about insurance or so on, you're worried about risks in particular as they shift up this side. What happens if emissions are higher than we think, or climate feedbacks are stronger than we think? What happens if we span out over here? If you're a pension fund and you want to pay out pensions in 30 years' time, you're worried if things happen faster than we think, so you don't want to invest in coal if that coal investment is going to quickly become a stranded asset, essentially, and lose its value. So you're worried if we move more rapidly towards, let's say, 2 degrees or 1.5 degrees. And that's more or less where I'm going to wrap up. I'll just leave you with this slide as I finish. But thank you.